Let us begin. This is going to be a solutions discussion or explanation of the answers related to the third exam that my 4B section took. Start with part 1, the concept questions. Our first question is to describe how to properly draw a free body diagram. A free body diagram represents the object of concern. We represent that object like a spaceship or a person with a dot. Dot represents that object. And then we identify what are the forces acting on that object, acting on that dot. We draw those forces in the appropriate direction in which those forces are acting on the object, and we draw them at the appropriate length that corresponds or is proportional to the magnitude of that force. For question 2, Newton's second law for why in deep space can have a non-zero velocity but remain in equilibrium. Newton's first law tells us that an object remains in uniform motion, and by uniform motion we mean moving with a constant velocity, unless acted upon by an external force. Here we have no external force. In other words, we're in equilibrium. Our net force is 0. If our net force is 0 and we're in deep space, we don't have a gravitational force acting on us, we don't have friction, we don't have any of that, then it remains at whatever velocity it was traveling at. By equilibrium, we mean that velocity does not change. That velocity could be 0. That velocity could be some non-zero number. In equilibrium, that velocity is just not changing. All right, and then for our third question here related to inertia, the car comes to a halt or stops because of the force that the wall puts on the car, bringing it to a stop, but you continue moving forward because you have inertia. You have a tendency to remain in motion unless a net external force acts on you, and that net external force would come from a seatbelt or maybe from you hitting the steering column, unfortunately, with your body. Question 4 is regarding Newton's third law. Newton's third law is such that if you push on the spaceship pushes back on you with an equivalent force of magnitude, but in the opposite direction. This is the same idea if you were to push against the wall while you're in a rolly chair, you would move away from the wall because the wall pushes back on you with the same force that you pushed on the wall. They wouldn't have the same resulting acceleration because presumably the two objects have different, the astronaut and the spaceship here have a different mass. Question 5, if you're at a stoplight and you're moving to the right, accelerating to the right, then you must have some non-zero net force acting on you that's causing that acceleration, and that net force is in the same direction as your acceleration, which our problem identifies as to the right. An object's mass on Jupiter, the mass is the same as its mass on Earth. The mass does not change despite a stronger gravitational field that exists on Jupiter. That gravitational field is something like 4 times stronger on Jupiter. When we're looking at terminal velocity, that's drag and weight. Those two vectors are equivalent in magnitude to each other, but opposite in direction. If an object's moving to the west, the frictional force opposes that motion. So if the object's to the west, then the frictional force must be in the opposite direction, which is the east. If an object has a 0 acceleration, that means the net force must be 0, right? That simply follows from Newton's second law and the first law. And then finally, if we're talking about the frictional force, we're concerned with the coefficient of friction, which depends on the surfaces, and the normal force is the other force we're concerned with, the other aspect of the frictional force. If we add mass to the system, that increases the system's weight. Increasing the system's weight will increase the normal force that's acting on the system, and thereby increase the frictional force. For our Lord's crucifixion, following his crucifixion and his descent into hell, immediately before he descends into hell and he's just standing on the elevator, he's in equilibrium because he's not accelerating. So these two force vectors that are acting on him, the force of the scale on our Lord and the weight of our Lord, are equivalent to each other, resulting in a 0 net force and a 0 acceleration. That circumstance is not true whenever he begins descending at some rate of acceleration. Because he's accelerating, there must be some net force. We would show that that net force is downwards in the same direction as the acceleration. And so the weight vector must be longer than the force of the scale on Jesus, so he's going to feel lighter. We resolve, mathematically speaking, Newton's second law for this picture that we have up here. This picture is the visual of Newton's second law, and then here we have the mathematics of Newton's second law. These are the two forces that are acting on Jesus. This force, the force of the scale, is in the positive, the weight is in the negative direction, so if we solve for the force of the scale, weight minus mass times the acceleration, because we have a negative acceleration, that's what this negative came from. Plug that into our formula, and we find that we have 310 newtons is the apparent weight of our Lord. All right, now we have a question relating to drag. So as our aircraft is taking off the runway, it has a strong force of thrust that's propelling it forward to the right, accelerating to the right. And then as it picks up velocity, the drag vector slowly becomes greater and greater until eventually when it's at its cruising altitude and at its cruising speed, that force of drag must be equivalent to the force of thrust that's propelling it forward. As such, it moves at a constant velocity and is therefore in equilibrium. We can use Newton's second law, again, to analyze these two forces that are acting on our object. Our object's not accelerating, so its net force is 0. So these two forces must be equivalent to each other, and that's visually what we see in our free body diagram. 220 kilonewtons of thrust must be equivalent to the 220 kilonewtons of drag that's in the opposite direction. In other words, 2.2 times 10 to the 5th newtons. By kilonewton, we mean just like 1 kilometer is 1,000 meters, 1 kilonewton is 1,000 newtons. All right, we have our two blocks here. In order to find the mass of each block, assuming that they're on Earth, in order to relate mass to weight, we're given their weights. We need the gravitational field. The gravitational field, we know because they're on Earth, is 9.80 newtons per kilogram. So if we take the weight divided by the gravitational field, we find that the mass must be 43.1 kilogram for the block that's on the table and 18.9 kilograms for the block that is hanging. Now, for part B, this is the slight trick to this problem, and that's why I provided this hint here, is if the hanging block was removed, would the top block move? In other words, would the system move at all? And the answer is no, right? If we cut that string there, the rope that's connecting those two, then the 422 Newton block or the 43.1 kilogram block that's resting on the table would not move. In other words, that block must not be contributing to the net force on the system. The forces that are acting on this block are only weight and normal. And this tension that's pulling it, right? The tension that's pulling it. Why is there a tension that's pulling on it? Because of this block. The weight of this block is not acting along the direction of the pulley. So it does not contribute to the net force of the pulley. It's only, or net force of the system. The only force that's causing the system to move is this block here. So the net force is due only to the weight of that block. The weight of this block is not along the line of the system. It's perpendicular to it, so it does not impact this block's acceleration this way. Now that we know the net force, we say, well, that force is acting on a system that has a total mass of 62.0 kilograms. So our acceleration must be 2.98 meters per second and down for this block or to the right for this top block. Finally, looking at the tension in the rope, we could use the free body diagram for one block, the 422 Newton block, or the 185 Newton block. It does not matter. We find that they are, at least to the degree of two significant figures, which would be more appropriate here. We see that 129 or 128 Newtons. It'd be easier to use the block on the top because in the x dimension, the only force that's acting on the block in the x dimension is that force of tension from the 185 Newton block. So that force of tension for a mass that we found was 43 kilograms. If that block is 43 kilograms, and if it's accelerating at this rate, then the force of tension must be 128 newtons. We can see that same thing here, but the diagram is a little more complicated for the block that is hanging. You have the tension force directed upwards and the weight directed down. Tension up, weight down equals the mass times the acceleration of the block. There's a negative sign there because this block is accelerating downwards, so we'll say negative. We still find that the net force, or rather the tension, is 129 newtons. Remember, tension was a good example of a force that is a Newton's third law of force, right? Equal but opposite direction. All right, for our car that's towing a boat, our first question is a kinematics question. We know the final velocity of 11 meters per second. We know the time in which it reached that velocity, and it started from a velocity of 0 meters per second. So we use our definition of average acceleration, which is the change in velocity over change in time, and find that the acceleration is 0.39 meters per second squared in the direction of the velocity, or plus, right? The free body diagram of all the forces acting on the boat and trailer system is here. If we were not to neglect or to ignore drag or frictional forces, then there'd be two more forces oriented to the left here, but we're told to ignore those. So the only forces acting on the boat and trailer system are this normal force that's pushing up against the weight from the ground onto the boat and trailer. that's opposing the weight of the boat and trailer. And then it's accelerating to the right. That's what we saw here. Accelerating to the right. Its velocity is changing, so there must be some force in that dimension that's causing that acceleration. And that would be the tension that's in the trailer or on the hitch. Finally, to find the tension that's on the hitch, if this is the only force that's acting in that dimension, we know the mass of the system that is undergoing some acceleration. If we have this mass undergoing this acceleration, then the force that's causing that acceleration on that mass must be, according to Newton's second law, 160 newtons of force in the positive direction. All right, Luke, super cool Luke, who's sliding along the tile floor in the hallway. Our first bit is to use kinematics to see what do we know. For a moment, ignore what's happening right here. We'll get here after we look at forces. So looking here, we know that his slide was 5.3 meters long. We know eventually he comes to a stop, so his final velocity is 0 meters per second. What we don't know, however, is his acceleration, his initial velocity, and we also don't know the amount of time in which this slide occurred. However, knowing the time is not relevant to finding ultimately how fast he was running at first. All right, so what we realize here is if we have two kinematics quantities, we need to find a third so we can solve for a fourth for our initial velocity. We can find acceleration by looking at forces. So now we look at Newton's second law. Here's our free body diagram of the forces acting on Luke if he moves this way. If he's sliding that way, then the force of friction is what's opposing his movement in that dimension. What's opposing him from falling through the floor due to his weight would be the force of the floor on Luke, which would be the normal force. If we look at the sum of the forces in the x dimension, we see that those forces are exclusively the frictional force. That equals mass times acceleration. That acceleration is in the negative direction. This is acceleration in the x dimension. We solve for that acceleration, which we find is irrelevant to his mass, is negative 4.1 meters per second squared. That's his acceleration in the x dimension. If we look at the y dimension, we were only able to find what this normal force was by analyzing the y dimension. So really we'd get to this point right here in solving. This I put in afterwards. So we'd get here, we don't know what the normal force is, but we know if we can find that, then we can find the acceleration because we know his mass and we know the coefficient of kinetic friction, which is 0.42. So if we go to the y dimension, we see that these two forces must be equivalent to each other because he's not accelerating in the y dimension. If they're equal to each other, we know that the normal force is equal to weight. Weight is equal to mass times gravity. So this normal force, this mass times gravity gets replaced into our normal force. So this divided by mass gives us our acceleration. Once we found our acceleration, we can return to kinematics. So now that we know acceleration, we need an equation that relates acceleration, final velocity, and the change in position. That is our third kinematics equation. Solving our third kinematics equation with what we know, we find that his initial velocity must have been 6.6 meters per second. All right, part 4, vectors. So to accomplish the Annunciation, St. Gabriel the Archangel descends from heaven to earth. He descends 32 degrees east of south. Here is south. East of south would be that way. So he goes from south and then towards the east. Right, so 32 degrees is this angle right in there. There's our descent velocity. There's our along the ground velocity, or the x component of his velocity. Those are the two projections of his resultant vector velocity. To find his rate of descent, that would be his vertical velocity or his velocity in the y dimension. In this case, a vector downwards as he's descending. We would use cosine because that side of this vector triangle, that side is adjacent to what we know, which is our hypotenuse and the angle. Adjacent to that angle is the descent velocity. Using a little bit of trigonometry, we find that his descent velocity must be 55 meters per second. We define descent velocity as change in position over change in time. That's how we define any velocity. In this case, it's in the y dimension. So what is his change in position in the y dimension? So vertically, if heaven is, this would be 30,000 meters above the earth, or 30 kilometers. That's directly vertical or directly in the y dimension. We can rearrange this equation and find that the change in time depends on the quotient of the change in position, change in y, over the velocity in that dimension. We find that that's 550 seconds. This would be 3.00 times 10 to the 4th meters divided by our descent velocity that we just found. And then we quickly convert that into minutes, and we find that that is 9.2 minutes of time it takes him to descend from heaven to earth. In the time that it took to him to descend to earth, which was our 9.2 minutes, how many kilometers along the ground did he travel? Well, we need to know what is his velocity along the ground. Here would be his velocity along the ground. The distance over time. We need to find his velocity. We know the time now. It took him 9.2 minutes or 550 seconds. To find his velocity along the ground, or the x component of his velocity, we have this same vector triangle again, except now we have the opposite side that corresponds to his horizontal velocity. So we need to use sine. We'll have 65 sine 32 gives us the horizontal velocity. That's what goes right here, right? Horizontal velocity times the time. That gives us the meters he traveled, divided by our conversion of 1,000 meters for every kilometer, gets us to 19 kilometers. All right. Finally, for our two forces that are applied to the tree stump, here's our free body diagram. We have our second force, force B, that is due south with a magnitude of 3,160 newtons. And then we have force A, which is 34 degrees south of east. So to the east, from the east towards the south, 34 degrees. The vector triangle that we have here, or the components, if we decompose that vector into two components, there's our x component, there's our y component. That x component would be the cosine of 34 degrees times the magnitude of this force, which is 2,240. That's why we have in the x dimension 2,240 cosine 34 degrees in the positive direction. That force is directed downwards somewhat, though, using sine, because this is the downwards force associated with this force vector, which would be sine because of the opposite side. So we use negative because it's downwards of that same force vector of sine 34 degrees. Force B is only in the y dimension. There's no component in the x dimension. It's only going downwards. So if we add those two forces together, we'd find that the net force is this value to the right and this value down. In other words, visually, if we added these vectors together, we would add this vector and this vector, so this guy is now this long. So we add these two over, right? And so here is our net force. There is our net force vector. This one that I just drew, that is our net force vector. Because we went over somewhat, and then we went down twice in terms of force, right? Here's over somewhat, and then down twice in force. Over somewhat, down once in force, down twice in force, from beginning to end. We add tip to tail, right? Tip to tail, all these are being added tip to tail. There is our net force. We find that net force using the Pythagorean theorem, once we've added our components, is 4,790 newtons. We would use the tangent of the opposite, which in this case is our y dimension. Here's our y dimensional components over the x dimension, which would be just the 2240 cosine 34. We find that that angle is 67 degrees. That is this angle right here. This angle here is 64 degrees south of east. From the east towards the south by 67 degrees. If you have any questions, please come see me. Thank you.